In this video, we're going to talk some more about the real series of polynomial functions. In particular, we're going to look at long division and synthetic division, and also talk about upper and lower bounds of the polynomials, and just kind of using some things that we can use to help check possible solutions that we could possibly have, positive, negative, and therefore real, non-real as well. So real quick, let's review long division. So if we want to do long division, remember that you always want to make sure that you have a placeholder. So obviously if we're dividing x plus 4 into our quantity x cubed plus x squared minus 10x plus 8. If we have any terms that are missing in between our highest term and our lowest term, just like we would do in synthetic division, don't forget to include the 0 placeholders in there. So long division, remember, just real quick to review in case you forget how to do this. Remember, you're looking for a value that you multiply x by to get you exactly x cubed. So I need to multiply x squared by x plus 4 to get this term to be exactly right. So I'm going to multiply x squared times x, which will give me x cubed. X squared times 4 will give me 4x squared. Remember that when you're dividing, what you multiply, you're subtracting. A lot of people make mistakes in the signs when subtracting. So I do, instead of subtracting everything, I make it adding the opposite. So it's like saying add the opposite of each of the terms that we had. That way I don't have to worry about positive and negative issues. So obviously your x cubes are going to cancel, and then you have an x squared plus a negative 4x squared, which gives me negative 3x squared. And I'm going to go ahead and bring down my next term. And then again ask myself the question, x times what will give me negative 3x squared? I know I'm going to multiply by negative 3x. Negative 3x times x is going to give me negative 3x squared. Negative 3x times 4 is going to give me negative 12x. Again, you can either treat it as subtraction, or again, I change it to adding the opposite, and then I don't have to worry about any of my signs. And then I end up with a positive 2x left over, bring down my last term of plus 8, and I know I need to multiply by 2, and I get 2x plus 8. And again, either subtracting or adding the opposite, and you can see that in this case everything cancels, so we have no remainder left. So in this case it divides evenly, and my final answer is just going to be x squared minus 3x plus 2. Again, be really careful if you have a problem like what I was talking about before. If you have something that has terms missing, remember that whenever you're doing long division or synthetic division, if I was setting this problem up, I would have x to the 5th plus 0x to the 4th plus x cubed plus 0x squared plus x plus 0 to show all possible terms here. Usually in long division, if you forget to have the placeholder 0 term, you can figure it out, because when you want to multiply, there's nothing to line it up underneath. But it's a good practice to get into, because in synthetic division, if you forget it, you get a totally wrong answer. So I'm not going to sit here and go through another problem with long division. I just wanted to show you how you would set that up to figure out and solve that out. Alright, obviously we know we can do synthetic division. This would be a problem I'd want to do synthetic division on, so let's go ahead and just review that real quick. Remember, again, if your factor is x minus 3, then your 0 is going to be 3. And when I'm setting this up, it would be 1x to the 5th, 0x to the 4th, 1x cubed, 0x squared, 1x, and 0. And then again, now it's much easier to do our synthetic division. So I bring down 1, multiply, we add, we multiply, add, we multiply, add, multiply, add, and then multiply, and then add. So in this case we do have a remainder, and if I wanted to write what the solution would be when I synthetically divide, which would be the same as if I do long division, remember this is your remainder, this is your constant term, this is your x term, your x squared term, your x cubed term, and your x to the 4th term. So my final solution would be x to the 4th plus 3x cubed plus 10x squared plus 30x plus 91. And when we go to write our remainder, in this case it's plus the quantity 273 over what we divided by x minus 3. Just a quick review, remember that synthetic division, if I gave you a problem like this, would you be able to use synthetic division to solve it? And the answer in this case, not directly, no. Your synthetic division has to be in the form x minus a, or some value there. If you could factor this into the two monomials, or binomials that are linear, you could do that. You could also find the zeros. If you saw them, they're going to be non-real zeros here. So you could technically do synthetic division with the non-real zeros. It's not as easy, but it's definitely possible. But this would be definitely one that I would resort to using long division if I just wanted to find out kind of quickly what the value was going to be. So remember, that has to be in that form x minus a or x minus c, whatever you want to call it, x minus some quantity here. And this has to be just a linear term. Alright, so how do we find the zeros? When we deal with polynomial functions, we're usually dealing with large degrees, and so finding possible zeros without a graphing calculator is, where do you start? So we want to talk about this idea of possible rational zeros. Let's think about what rational zeros are going to be. Zeros that you can write in some sort of fractional form. So in order to figure that out, we need to know two things from our function. The first thing is factors of the constant term, and the other thing are factors of the leading coefficient. And anything that I could write as a fraction of these two is going to be a possible rational zero. It does not mean it's going to be a zero, it just means a possible value. This helps eliminate any values that it can't be, which makes really nice. So let's look at an example here. So let's say this is my polynomial function. Let's look at our constant term. Well, our constant term is the term without the variable on it, so our constant term is -2. The nice thing with -2, there's not many factors. Obviously, positive or -1, or positive or -2. Again, depending on which ones you're multiplying by. Then we look at our leading coefficient. In this case, it's 6. And do be careful. Make sure it's in highest degree order before you just jump to that, because the leading degree needs to be one of the highest exponent here. So 6, there's a couple different options, plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. What the rational root theorem says is if you have some possible zeros that you can have, they're going to be in this form of one of the factors from the constant term over one of the factors of the leading coefficient. Because we have positive or negative, I'm just going to include that on my solutions as well. So one possible solution, well, 1 over 1, which simplifies to 1. Very easy. 1 over 2, which should be plus or minus 1/2. 1 over 3, which would just be plus or minus 1/3. And 1 over 6, which would be plus or minus 1/6. So those are all our values with 1 as our constant factor and one of these values for our leading coefficient factors. We also have the value 2, 2 over 1, which would simplify to plus or minus 2. We'd have 2 over 2, which simplifies to 1. We've already got that. There's no need to list it again. 2 over 3, we don't have that one, so plus or minus 2/3. And then, of course, 2 over 6, which simplifies to 1/3. We already have that factor. So these are all possible zeros that you could try. So why does that help us? Well, if we know, first of all, that there is going to be a real zero in there, and it is a rational zero, it gives us some values to try. And remember, we talked about the remainder theorem. That's a quick way to see if you've got a factor or not. So plugging in the value into the function and seeing if you have a remainder of 0 or not. It's just a quick way to do this, especially when you don't have a calculator handy. Obviously, some values are going to have more options than others, but it's still a good starting point. So remember, if we want to determine if it's a solution or not, once we've figured out some possible solutions, remember we want to use the remainder theorem. And that basically tells us that what we want to do is take our value into our function, plug it in, and if we get a remainder of 0, then we know it's going to be a 0 or it's going to have a factor. Once we find a 0, how do we find the rest of our solutions? Well, remember, we've talked about synthetic division to help us work even further. If I know it's a 0, then I can use synthetic division, and usually from that point, hopefully it's factorable, or maybe there's actually another 0 that we can find. We'll look at some examples of this in class to help you kind of show you what to do. Remember that sometimes when you do the rational root theorem, it's helpful. This would be an example where there's just way too many factors. Obviously, your coefficient or your constant term here is -40. There's a lot of values that you could plug in, you know, plus or minus 1, 2, 4, 5, 8 goes into it, 10 goes into it, 20 goes into it, 40 goes into it, and then you've got 9, and of course you could have values of 1, 3, and 9. You can see there's a lot of different values you could have. That's a lot to work through, and usually if I'm asking you to list all the possible values, I'm not going to give you something this crazy, and this is really where we kind of want to use our calculator to kind of sort of help us down. But there is something else we can do to help us determine, first of all, how many solutions we have in terms of positive and negative, and that's what we want to look at next. So when they have too many factors, let's see if we can narrow down the solutions possible. So we've got something called Descartes Rule of Signs, and there's two parts to it. The first part says that the number of positive zeros is either equal to the number of variations of sign of f of x or an even integer less than that. Let me make some sense of what that is by looking at an example. So here's our function. F of x equals 3x to the third minus 5x squared plus 6x minus 4. When I look at the signs in terms of the terms, I've got a positive, I've got a negative, I've got a positive, I've got a negative. What we want to look at in terms of our function f of x is how many variations of sign do we have? How often does it change from positive to negative or negative to positive? Well, here's one variation, right? From positive to negative. Here's another one, negative to positive. Here's another one, from positive to negative. So we have a total of 3 variations. So we have 1, 2, 3 variations. Descartes' Rule of Signs says that a possible number of positive zeros that we can have would either be this number, 3, or an even number less than that. So it could either have 3 or 1. And we don't go down any further because obviously we can't have anything less than 0. So in this case, it's just going to be 3 or 1 solutions. So it's possible to have 3 positive solutions, or we could have 1 positive solution. And then we need to look to see how many negative solutions we can have. That's the second part of Descartes' rule. So Descartes' Rule of Signs says the number of negative zeros is either equal to the number of variations of signs of f of negative x, or an even integer less than that. Let's look at an example again. So here's our function f of x that we had earlier. Let's talk about what our function f of negative x is going to look like. Remember, this the degree that's going to tell us if the sign's going to stay the same or it's going to change. So if I put in a negative and I cube it, we know the sign's going to change here. So this is going to become negative 3x cubed. When I put in a negative x into something that has an even degree, it's going to stay the same. So this is going to end up being minus 5x squared. Odd exponent, going to change the sign. No value for x, not going to change the sign. So this is f of negative x. So we go from a negative to a negative to a negative to a negative. 0 changes of sign here. So this tells me that I have 0 negative solutions. That helps a lot. Now I know from this function, if I have any rational zeros or any positive zeros that I'm going to have, they're all going to be positive if they're not in non-real solutions. So 0 negative solutions is what this tells us. So let's put this all together. So if I want to summarize the total possible solutions we have, 1, we know, first of all, there's going to be 3 total solutions. And that's because our highest degree says the maximum number of solutions is going to equal the degree. So we've got 3 total solutions that are possible. One option is all 3 are positive. That was one possible option, right? The other one says, well, instead of 3 positive options, there could have been 1 positive option. Well, if there's 1 positive option, that means that there's possibly going to be 2 more options. But we just discovered that 0 of them were going to be negative. So if there's 1 positive outcome and there's no negative outcomes, what are the remaining 2? The remaining 2 would be non-real solutions. So we know that our answer, when I go to figure this out, is going to have either 3 positive solutions or 1 positive solution and 2 non-real solutions. And the easiest way to figure that out is just take a look at the graph. If you can see that it only crosses the x-axis at one time, most likely it's going to be this one, unless of course it's multiplicity of 3. But I can pretty much look at this function and recognize that that's not going to happen. So most likely we're going to see 1 positive solution, and that means the other 2 are going to be non-real. Once we've got this positive solution, finding these 2 non-real is actually just as simple as using the quadratic formula. So this really won't be hard to do. Let's look at another example. So let's summarize the possible solutions. We know that g of x, so we go from a positive to a negative to a negative. So I have 1 change of sign, no changes of sign. So for positives, there's only 1 possible solution. So 1 positive solution because we can't go down any less than that. Now let's look at g of negative x. G of negative x, well, if I put it into a negative with this odd exponent, it's become negative x cubed. When I plug it in here, that's going to stay the same. Nothing to plug in here, so that's going to stay the same. So I've got a negative, negative, negative. 0 changes of sign. So this tells me I'm going to have 0 negative solutions. So let's summarize. We know we're going to have a total of 3 solutions. So it's either option 1 positive, and that means the other 2 are going to be non-real, since there's none that are going to be 0, or, hey, that's the only solution. So we know there's only going to be 1 positive solution and 2 non-real solutions. Let me give you one to try. go ahead and pause this and then figure out how many positive, negative solutions are possible, and then list the combinations of positive, negative, and non-real solutions. So go ahead and pause this now, and then go ahead and solve it, and we'll check answers. All right, let's see how you did. So when you looked at your positive solutions, you saw that it could either be 3 positive or 1 positive. When you looked at your negative, looking at f of negative x, you saw that there was possibly 1 negative. So that tells us that there's 2 possibilities. 1, because we know that the sum has to be 4, we could either have 3 positive and 1 negative. There's our 4 solutions. Or 2. It could be 1 positive and 1 negative, and then the remainder are the 2 non-real. Do we have any other possible solutions? No. In this case, we know it's either 3 or 1 positive. We consider both of those options, and it includes the 1 negative all the time, and they always have to sum to 4, so there's no way it could be anything else. So it's got to be one of these 2 options. One of the important things to note is that it's really important. When you talk about non-real solutions, remember when we take the square root of a negative number, we always have that plus or minus. So non-real solutions always come in pairs. You're never going to have an odd number of non-real solutions. So when you're listing out your combinations, be very careful. If you get something that says 3 non-real, something's totally wrong. You should always get an even number of non-real solutions.